Welcome. In this video I'm going to give an introduction to using Simulink. So we're going to run through the modelling of an open loop system and also the modelling of a closed loop control system. So you can see the form of the two models here. So at the top here we've got our open loop system where our actuator and process are represented by a second order transfer function. This is modelled in the continuous time. And you see our step input here is a unit step input, so 1 over s. And our output here. So our output is generated via the input multiplying by the system. So we'll go through how to model this and also to generate the relevant data, so input and output data. And then our closed loop control system here, you can see, so the open loop system is the same. So our continuous time system. However, we've got this feedback here from the output. We've got a sensor here, value of 1, and into this summing junction we've got a negative value. So we've got negative unity feedback. Okay, unity because we assume in an ideal sensor, i.e. a value of 1. Our reference, so this is what we desire from the control system, we're modelling again with a unit step input, so 1 over s. So in the time domain that's effectively a 1, so what we desire is 1. Obviously our output, this is what we're effectively feeding back. Compare with the two, so reference take away output, you form your error. And then your error then multiplies by this proportional control gain. So you can see at the moment this is just a value of 1. We'll show you in the simulation how you can change this and how it affects the system output. And then obviously the error multiplied by the proportional gain becomes your control output, which is your input into your system. And again, we'll show you how to model this and also then to generate the relevant data and compare the reference to the output. So you can talk about things such as steady state error, and then the effect that change in the proportional control gain has on the steady state error. What I have here is the graphical user interface. So what we're going to now do is go into Simulink. So if you go to the top bar here, you can see here Simulink. Click on that and then you'll see it opens up this Simulink start page. If we then click on blank model, this will then give us the blank, well effectively a blank model as it says, whereby we can construct our Simulink diagrams. So to be able to actually construct the diagrams or the block diagrams, click into Library Browser, so you can see here Library Browser, and it'll open up this tab here. And this contains all the blocks that you'll need for your simulations. So to begin with, I'm just going to start by simulating the open loop system. So what I'm going to get is a transfer function, an input, and something to capture the output data. So if I go to, you can see here Simulink. If I go to the ones you'll likely use the most is commonly used blocks, continuous, sinks, and sources in terms of the tabs. And over time you'll get familiar with using these, so I wouldn't worry too much about understanding what's in every single one. So Simulink, continuous. Then if we go to transfer function, so you can see this here, click and drop that onto the blank model and you'll see it'll appear. What I'm also going to get is, if I go to sources, I'm going to drop over a step input. So you can see here, step input. Drop that over. And then I'm going to go to sinks, and I'm going to drop over a scope. A scope is effectively, as you'll see, it's your output data from the simulation. So if I put that there, here, and literally just to connect the blocks, just click on one, drag until you join the other arrow. It's as simple as that. Okay, so, and simply just to undertake the simulation, just click run here. So run. Okay, then if you double click on here, you'll see your output. Okay, you might want to compare your input with your output. So what you can get is something known as a mux. So in commonly used blocks, get mux, copy that over, and break that line, just click delete. Oh, no troubles. Delete. And then just join that up there. Then what this will do is it'll within the scope it will show your input signal and it'll also show your output signal on top of each other. So click run. So you can see there input data and your output data. How about at the moment it's a first order transfer function. How about if we wanted to make this second order? So we go into here, double click, so numerator coefficient and denominator coefficient. When you've got two coefficients on the denominator, it'll assume it's first order, so let's add another one. So it's got three coefficients, and you'll see, I can just move this across, you'll see now it's second order. If you want to zoom in, by the way, click that, that'll span you in. So now it's second order. Okay, the coefficients don't all have to be 1. You can change them, so you can see 1, 2 and 3, apply. And you can see 1 over s squared plus 2s plus 3. And you might want to change the numerator coefficient as well, so let's change that to 3. Okay, and apply. Okay, so if you had a third order, which is unlikely, well, you could do, then you can see, same sort of idea, it's going to go up into highest power being third order. So that's nice and easy, okay, how to change the coefficients of the transfer function. Okay, click OK. So that there is your open loop. So we can add a label here if we want. So open loop system. So how about now if we're going to start looking at the closed loop. So I'm just moving this around. So that I just use my mouse to zoom in and out the scrolly thing. So now I want to do a closed loop control system. So what I'm going to do is I'm going to take this. I'm just going to go right click on it, go copy. So I want to use exactly the same transfer function and click paste here. Okay, and one thing I should say is you can go on these and you could, so at the moment this is a unit step input, this is your output, and then this is here is your system. So you see now we've labelled these. Okay, so by default, I should say that this is a step input. By default, MATLAB will apply a unit step input. So effectively a value of 1. Okay, so we've got our transfer function here. We need some further blocks, because what we're going to do is set up the feedback control system. So let's get 2 gain blocks, and you'll see why. 2 gain blocks. Let's get a scope again. Let's get a step input. We'll talk more about these step inputs in a minute. And then what we need is a summing junction. So you can see commonly used blocks, sum, drop that across. Okay, so let's put that there. We're going to put an ideal sensor in the feedback. So if I right click on this and then go rotate flip, I'll go flip block. Okay, you'll see it's flipped the block. So what we want to do is, because we've got a feedback here, so the flow is obviously from right to left. In this particular one, obviously the flow of the signals from left to right, so that's fine. Okay, so sine. This, okay, because what we want is negative unity feedback, or negative feedback. So if we put a minus in there, just click apply to check, you can see it's changed the right one there. Okay, so if I was to accidentally, say for example, select that as a negative, you can see it's put them both as negative. So sometimes it's useful to just use the apply button, just to check. You can see now I've really messed up, just to check what you're doing beforehand. Okay, so click OK. Join this all up. And what we're going to do, we're just going to, as we did up here, let's just label a few things. So this is, we'll just call this KP, so your proportional control gain. We'll call this here our system as it is. Here this, we'll call it system, just put 1. This we're going to put output. You can see it doesn't like that because there's already something called output. So put output 1. Here we're assuming an ideal sensor, so let's just put ideal sensor, because it's got a value of 1. and here again what we've got is a unit step input. I'll just put that on 1. Okay, so we could just squash this all, make it a little bit tidier. Okay, so we've got the same transfer function, proportional gain of 1, a unit step input, and then the output and ideal sensor. So as we did before, we can just simply click run, and if we click on the scope, we can get our output. So you can see there, the final value of the system is 0.5. Okay, so as we did before, maybe we actually want to put a mux there to compare the input to output. And another way to actually get the blocks, once you're familiar with them, is just double clicking on here and just typing in what block you want. So I'm aware that it's called mux. You can see there it appears. So just break that line. Join it up there, and that's then going to compare the input, or the reference I should say, to the output. So you can see there, the reference is 1 and the output is 0.5. That's one note actually I'm just going to make, is I'm just going to rename this reference, just not to confuse you. Okay, but the reference is a unit step input, just be aware of that. So reference, okay. So that's cool. So then, for example, if I increase the proportional control gain, so maybe if I went up to 10, click OK, click run. Oh, what you can see now is the final value of the system is about 0.9, but there's more oscillation, or you can see this kind of oscillation on the response. Then if I increase this maybe to 25, click apply, click run. What you'll notice is that there's again more oscillation, but maybe a smaller steady state error. So a steady state error, and there's a difference between the output and the reference. So what you've noticed is when you're running this, you notice that you're getting just the open loop system. You'll get no, well, it's not so common to talk about steady state error, but you're getting, you can see 1 in, 1 out. Here now, in terms of proportional control gain system, you're getting a difference, so a steady state error between the two signals, so the reference and the output. And as you increase proportional gain, it reduces, but you introduce more oscillations on the system response. So just one final thing, so reference. So I'm just going to talk about this block. So this is the unit step input block, or the step input block, not the unit step input. So unit step input when the final value here is 1. So you can see by default MATLAB says step time 1. So you have that slight offset in terms of the step time. Is good for just really illustrative reasons when you're looking at your plots. Initial value 0, don't worry about that, and then final value of 1. Hence, when you've got final value of 1, it's a unit step input, and then sample time. Don't worry about that at the moment. So I could change this to 2. Okay, and then click apply. So now I've effectively got a value of 2 acting as my reference. And then if I click run, click on the scope, you can see now my reference is 2. And you can see the system output now is, I don't know, 1.8, something like that. So, another thing, in terms of your simulation time, it might be such that you want to actually increase it, because you'll see by default, it's 10 seconds every time we run the simulation. That's because the stop time here is 10 seconds. So you could just increase this maybe to, I don't know, to 15 seconds. And then click run. And you'll see the same, you'll see the time changing out here. So you'll see it's 15 seconds. Obviously the system response is the same. So that concludes me on this video. I hope you found it useful. Thank you.